Hello and welcome to the SolidWorks Simulation Tips and Tricks webinar. My name is Kurt Curtin. I'll be with you today presenting the topics. So let's get started. For the webinar, I'm going to show you a few things on the web that are important for support and otherwise using SolidWorks in simulation. And then we'll get into what I like to do as a top 10 list for the tips and tricks and highlight some of the new features for 2013 simulation, and then end up with a question and answer session. First, in terms of the web items, the knowledge base is one I like to bring up. If you go out to solidworks.com, there's a login link at the top of the screen there. Brings you to the page shown here where you can log into the customer portal. If you haven't done so already, you can create a login for it and access a lot of features, including the knowledge base, your SRs that have been reported on your behalf, and other items of interest. So make use of that. And we can also access that same site through the SolidWorks interface within the SolidWorks Resources tab of the task pane on the right side of SolidWorks. So hopefully that's some good information to allow you to access those items. The other item I wanted to mention is called My SolidWorks. It's a relatively new release from Dassault Systems. Actually, I believe it came out last month, whereby it's a collection of the items related to accessing things like the SolidWorks forums, featured articles, support topics, those types of things that are coming directly from SolidWorks and the SolidWorks community. So take advantage of that, check it out. And I believe your customer portal login is all you need to get into that. That's my.solidworks.com. All right, so let's get into the meat of the program today. We're going to talk about a top 10 list. I like to do it in this format, kind of do a countdown. So starting it off for number 10, what we have is the use of true scale for studies where contact is involved. Here's a simple example of a set of pliers gripping a bar stock, and if we were to set that up in simulation, it might look something like this, where the bar stock is eliminated and replaced with a fixed restraint on the end of the pliers, and we have the load squeezing the plier handles. So if, for example, we wanted to simulate the squeezing of the handles such that we collapsed them and they touched on the end there, where you see some small split lines on the pliers, then it would be important for us to use a true scale. So here's a deformation scale of 2, where you actually get what appears to be interference between the plier handles. And anytime you use contact, you really want to use the deformation scale of 1, or what we call true scale, within the interface. And to access that, you edit the plot in question, and then go into the deformed shape mode and switch that over to true scale. So that's number 10. Moving on to number 9 is the use of folders to manage the simulation tree. With some projects, the simulation tree can get fairly busy. This is one example of a pressure vessel analysis in which the contact sets folder has been expanded to show all the contacts that have been set up. The 4 that are highlighted are unique to this steam inlet flange. So to clean things up, we could make a subfolder here on the contact sets and drag and drop those into that folder. So here's a shot of where that's been done, and it's been done for the other contacts. Those have been grouped according to the components that they're associated with. So helps to clean up the tree, make it a little bit more manageable. And as you can imagine, you can get quite a few items in there. So here's a screenshot of the parts folder. You could do the same thing here, and I've shown where you right-click on the parts folder and select the Create New Folder icon there for that. So keep that in mind for organizing the tree and keeping things a little more tidy. Moving on to number 8. Is the use of workflow-sensitive sensors within SolidWorks and simulation. I've done some polls, and I've found that there's not a lot of use of sensor functionality within SolidWorks, so I wanted to kind of highlight that for you. If you notice in the tree shown here, we've got results for a temperature analysis, thermal analysis for a electronic component on a heat sink. And the top section, of course, shows our SolidWorks tree. And I've highlighted the sensors folder expanded with a few items already in there. Of course, we have the lower section of the tree, which is the simulation tree. So we can use sensors in a variety of ways, from tracking mass properties of the model within SolidWorks, looking at dimensional values, and just an overall sort of a monitoring of things. We can also do that in terms of simulation. And you see the last one on the list there, that's the thermal 1 simulation, shows the maximum temperature for the model at 179 or 180 degrees Celsius. You also see a couple above that that are called workflow sensitive sensors. And this allows you to pick points within the model, and they can be buried within the solid itself where you're actually monitoring things. So what I wanted to do is to switch over to the SolidWorks interface and just show you how that might be done on that model. Here's a view of that model, and showing just the SolidWorks tree now so we can understand how these sensors are set up. So if I show my sketches, you'll notice I've got a sketch in here that's buried within the solid for the integrated circuit chip. And I've got some sensor data set up for the lower half of this grid, if you will. And I want to demonstrate how we can set up more points and sensor points to monitor the upper half. So there's an existing set of points here, 1 through 4. I'll turn on the view of that. And these points were what were used for this first case lower sensor. Let's create the points and the sensors for the upper half. Using the reference geometry functionality, I'm just going to go and create some points now. And you'll notice the various ways in which you can apply points. This is SolidWorks functionality. I'm going to use the intersection function, and I'm going to zoom in here. And I'm going to use the existing lines in the sketch here to create 5 additional points. So there's one. Just selecting the combination of intersecting lines to get the location of the point. So picking those, oops, didn't want to get the face, want to get the line there. And there you have those. Let's go ahead and put one more. Okay, so now we have additional points that we can use in our sensor setup. So moving over to the sensors folder, I'm just going to add one, or add 5, that is. Go ahead and pin the dialog box here. And notice how our whole list of sensors that we can set up is shown, where we can, like I said, use sensors for mass properties of the model, dimensional information, etc. So I'm going to switch over to the simulation side, and the different data quantities we can establish are related to all of the study types that are available to us. So for instance, we can monitor the overall stress value, the model max. We can monitor, if I go into the thermal, we can monitor the maximum temperature. That's how the one that was set up that you saw there, the last one. But what I'm going to do is use this workflow sensitive capability, and I'm going to pick the points of interest where I want to monitor things. So 1, 2, 3, 4 are already existing. I'm going to go to this one and apply that one. Let's see here. Doesn't want to take it. Let's try it again. Point. Let me start that. Oh, okay, it did take it. All right, so a little bit of a hiccup there. Let me go ahead and just get rid of these. Try that again. It's a little bit odd. but I'm going to go back to simulation data, workflow sensitive, and pin it. I think it's actually recording it. Let me just double check that. Yes, okay, so there's that one. Just make sure here. Yes, something was wrong with my graphic display, so it's actually applying them, but they're not showing up that way when I actually do it. So I'm just going to do one more. And actually got that whole assembly in there. Okay. There we go. All right, so here's a couple more as I set those up. And let's go ahead and check out the results in this study relative to those sensors. So we have 10 and 11 here. Let's check that on this steady state results folder. So we can turn off the icons here, the simulation icons. Just going to do that to clean up the display. And then I can take a temperature plot, show that, and notice that the maximum temperature is about 180 degrees, and that is actually buried within the model itself, within the integrated circuit chip. So if I probe that, I can look at the values at my sensor points. So using from sensors, here's one of the new ones that I created, and there you see the value for that particular point in the model. So that is the use of sensors within simulation, and they're quite useful for other areas of simulation. For example, the design studies that allow you to do several what-if scenarios. We can monitor things in the design studies using the sensors. All right, so let's jump back over into the presentation and move on to number 7. Thermal stress study is number 7 on the top 10. So using the model that we just looked at as an example, if I were to set up a static stress study, I can look at the effects of the temperature distribution within that model in terms of the stress that is generated due to thermal expansion. And the way I do that, the way I access that information, is to right-click on the study name and go into the properties of the study that you see here in this window. And we have a tab for flow and thermal effects. We can bring thermal information in from the existing thermal studies. As you see here, I've selected to bring in the steady state thermal study. Note that we can also bring that information in from the SolidWorks Flow Simulation program, if you have that. We tell the program where the reference temperature is for zero strain in the model, and then it takes it from there using the coefficient thermal expansion for each material and setting up the resulting stress field for you. Note also that we can bring in pressures from the flow program as well. In the lower part of that screen, you see that. That's thermal stress study, so make use of that. Let's see. All right, so moving on from there, number 6, force balance check. It's always best practice to determine whether or not you've actually put in the correct loading, say when you're doing a static loading of a part or assembly. Here's a screenshot of a bridge that weighs about 1,300 pounds, and it's supporting an 80,000-pound load. So this screenshot shows the setup and results for that study with the loads applied. You see the gravity load applied in the Y direction and the force of 80,000 pounds applied to the bridge. So we also have in green the areas that have been restrained to fix the model in space. So what we can do then to check on things is to right-click on the results folder and go into the result force dialog box. And when we do that, we get a graphical representation of the forces involved, and we get this chart that tells us what our resultant forces are for those areas that we've selected as restraints. And here you see confirmation that we have approximately 81,300 pounds in a reaction load for the checking of our input. So very important to do that, to do the due diligence for any simulation study. Just like when you do convergence checks, it's always important to make sure that what you put into the model is what you wanted to put into the model. And that's how we do that. So moving on to number 5, we have the transient response plot. This is a functionality that's available for any study that has transient data in it. Simulation Pro gives us the ability to simulate transient thermal studies, and Simulation Premium allows us to do linear dynamic studies where we have an input that might be, as shown here, where we have an acceleration spike or a shock load. So anytime we have that, when we get into the results mode, we can see how the results look here in terms of the transient nature. So this is a shot of the maximum displacement, maximum resultant displacement. And as expected, you see that occurs at the midspan of that bridge. And so picking a point there at that midspan location where it's maximum, we can go into the report options down here at the bottom of the property manager, and we can use the response plot button. And when we do that, for that node, we get the time history for the resultant displacement. And you see that shown here, how this bridge would see the peak and the spike and then resonate a little bit as the vibration proceeds after a result of that spike. So that's the transient response plots that are available to us within Simulation Pro and Simulation Premium. Moving on to number 4, a new feature for SolidWorks Simulation 2013 is the use of shells and a 3D, or actually the representation of shell results in 3-dimensional display. So here's a example of a pulley that might be used in an automotive system to serve as the adjustment, the tension adjustment on the serpentine belt. And looking at that in terms of analysis, it's very conducive to using a shell mesh on that, a surface mesh where we have shell elements that are 2-dimensional in nature. And as a result, we're going to get output that's also 2-dimensional in nature. So taking a look at a symmetric model representation of that pulley with the load applied in this one upper section, when we go and set up our shell mesh within the simulation, we're going to get, oops, went away from the screen there. Sorry about that. Let me get back to where I was. Hit the wrong button there. Sorry about that. So when we look at the shell representation of the mesh, we'll see a color coding. We get a red surface and a gray surface. And what those are related to are what is referred to as the top surface and the bottom surface of the 2-dimensional shell mesh. So a little bit more background. The thickness is represented in the shell mesh formulation. It's not explicitly captured with the mesh itself. So we get these 2D elements, and then the thickness is built into the formulation. So in the options for the study, we have an indicator of the color that represents the shell's bottom face. So we have to do some bookkeeping up until the 2013 release. It's a little bit cumbersome to manage the results because of this top and bottom face of the shells. So let me jump over into SolidWorks and elaborate on that a little bit. So here is the axisymmetric model of the pulley. And this is the setup of it. As I indicated, we've got a pressure load up here applied to the top surface to represent the belt tension. And then we've got the symmetric boundary conditions along the edge that have been cut, and then a fixed face here in the middle. So whenever we deal with generating results plots, you'll notice I have a von Mises top and a von Mises bottom. If we show those, show the von Mises top, you'll notice that we have, let me do one switch here. It's already been converted over to the 3D. I'm going to pop back over into the shell. So looking at the results in terms of the typical output that we've gotten up until 2013, we get information as shown here. I'm just going to turn off the symbols for the boundary conditions. And notice that my plot is showing me the top stresses. So on the top fibers of this thin pulley member, this is the stress that we get. And if you notice, as I rotate it around, it looks the same from the top or the bottom. That's because it's showing the same thing. There's no difference depending on the way you look at it. So 64, well, 65 megapascals. If I show this bottom stress results, this one has this has a high deformation scale. That's why you see it deflecting differently. But this is the stresses on the bottom face of the shell, and now we're up to 80 megapascals. There again, same front and back, looking at the same result. So before 2013, what I had to do was to make sure I looked at all the plots to capture the information that I was looking for. And another nice feature that allowed us to do that was using the split viewport. So if I split this two views vertically and unlink the views, let's see, oh yeah, they're already unlinked. Sometimes they come in as linked. Let's go ahead and show those two side by side. So on the left we have the bottom stresses in a deformation scale of 46. I'm going to edit that, jump that down to true scale. And then on the right, I'll just switch over there and show the top plot. And notice the difference there. So we've got the 64 megapascals and the 80. So that's the way we have to carefully look at the results so that we make sure we get the whole picture. But in SolidWorks 2013, we can easily convert these plots to show the results on the three-dimensional representation of the model. So if I edit the definition of this one, and I go over to the advanced options and I render that on 3D, now we get a representation that contains all of the information. So notice that the maximum 80 is actually on that inner surface, and then I have the 64 approximately on this outer surface. So 2013 allows us to see all that information on one plot. Very handy, for a very nice addition to the software. So moving back into the slideshow here, let's go to number 3 on the list. Beam elements. If you haven't used beam elements in your simulation, it's definitely worthwhile to consider, because some situations like this frame are very conducive to using beams over solid elements. So typically, any extruded member, could be straight or curved, excuse me, any extruded member is going to be able to be converted to a beam, as you see here with a right click. You can convert those over. Beams are automatically generated for geometry that was created using the SolidWorks weldments tool. So that's one thing to keep in mind, is that if it doesn't come over as a beam, and it should be, we can do that with a right click. So you see that here where we have the main frame members switched over to the beam mesh, and we have the solid members that remain. That would be these 4 feet at the bottom and the 3 gusset plates that tie the beams together. So in this case, we have a mixed mesh of elements, and SolidWorks Simulation can mix all 3 types together: solids, shells, and beams. And if we were to mesh that, here we see the representation of the solid and beam mesh, and that's very much less overhead involved in solving this model. And in fact, some models, it's nearly impossible to mesh with solid elements when you have these types of members. The cross-sectional thicknesses are just too small to get a solid element through it. And if, in fact, you're able to do so, if you're able to mesh the beams with solid elements, you're likely only to get one solid element through the thickness, and the requirement for getting accurate stress results through the thickness of any member is that you would have at least 3 high-quality elements through it. So very important to make use of these beam elements as necessary. All right, for number 2, as we had for the shell elements being able to be mapped over to 3D, we can do so as well. We've been able to do this for a little while with beams. So looking first at a solid representation of this structural member and set up as a cantilever beam, if we look at a deflection plot of that, this is what we see in terms of solid mesh elements. So you get the full view, the real profile of the element itself, or of the member itself, and we're looking at 0.05, approximately 0.05 inch deflection at the tip. If we were to convert this over, as I did on the previous frame structure, if we were to convert this over to make use of the beam functionality, we would see something like this by default. So it's a generic profile that gets mapped over for the mesh and for the results. It's just this cylindrical profile. So, and that applies to any member. Now we can you can look at the results here. We do have pretty good agreement of the deflection results there, and I can in fact switch over to render this information on the beam profile. If I use that option within the setup of the plot, I'll get something that looks like this. So we get a lot more accurate representation of the geometry with the same information that we had before on the more generic beam plot. So that's mapping beams into 3-dimensional representation. Here's another example of a little frame for some type of a Baja car that has some tubular, some square and circular tubular members. Just looking at one of the results plot where that's been done, you see at the ends where those rectangular or square members are, they are captured that way in our results plot. All right, so number 1 on the top 10 list is quite important, and its functionality that's available with SolidWorks Professional, Simulation Professional and better. And it's the use of 2D simplification of your models for simulation to save overhead, and in some cases to run studies that would be prohibitive to run with solid elements. So when we set up studies within simulation, if we have Simulation Professional, you'll see the option down below there for using 2D simplification. And this is available to us for static, thermal, and nonlinear study types. So all 3 of those can be mapped over to use 2D simplification. And the way it works, when you select that option, you'll get a second window that allows you to finalize the setup, because we can pick between 3 types. We can have plane stress, as shown here, and this little simple representation of a wrench, and then a plane strain formulation of the problem, which would be something like a long member, like a dam, where you're taking a cross section through the dam. And then the third being an axisymmetric type of a setup for those types of problems like pressure vessels, cylindrical type shapes. And what I want to do in this presentation is to show you the axisymmetric functionality for 2D simplification on this pressure vessel lid that's sealed to a flange with a couple of elastomeric gaskets. So we'll take a look at this, and we'll see the benefit that can be afforded by using 2D simplification in this problem. Okay, so looking at the full solid mesh model, getting an idea of what it takes to solve this type of a problem. What we have here is a von Mises stress plot for a linear static study. So we've got an indication of the number of elements that would be involved for this very coarse-looking mesh, as you see in the top left. So for very coarse mesh, we have 90,000 elements at a solve time of 43 minutes. So as I mentioned before, it's important to have a couple of elements through the thickness of any member where you're trying to resolve stresses. And you'll see here on this the view of the mesh, there's only one element through that thickness. So this solved in 43 minutes, and it's not a very good model, just looking at that from that standpoint. So the next logical step is to use solid elements on a 20-degree slice, or some pie-shaped slice of the model. You literally take a cut out of the model in SolidWorks, and then you just represent that portion of it. And you can make any angular representation of the slice through here, as long as you're not getting distorted elements there up at the center area. So a 20-degree slice would be acceptable for this. But there again, we have a fairly coarse mesh, as you can see. And when we look at the results, we've got a lot less overhead, 24,000, 25,000 elements, 11-minute solution time for linear static. But let's take it to the next step in terms of the 2D simplification. 2D simplification basically takes a slice, an infinitely thin slice through the model, and it meshes that slice with shell elements, as I showed you with the pulley. So using those 2D elements, there's a lot less overhead. As you see here, we have a pretty good representation of the geometry with the mesh that we've created, and we have about 1,500 elements, and this solves in a very quick 3 seconds of time. So there again, a linear static solution is going to be very quick for this. Get a lot of benefit there. But we are really needing to go into a nonlinear analysis if we really want to capture the behavior of those elastomeric O-rings. So that adds a lot of overhead to the problem. And now you're going to really see the benefits of the switching over to 2D simplification when we get into that realm. So I'm not even going to show you any information about the full model, because it's just prohibitive doing any kind of accurate model with a nonlinear static. So we'll start off with a 20-degree slice. There again, a very coarse mesh, very coarse representation of the problem. And when we look at the results here for a nonlinear static, whereby we're calculating contact information as well as a nonlinear material behavior, with this 25,000 element system, now you see our solve time goes up to a whopping 2 hours, 50 minutes, nearly 3 hours of solution time. So quite a big increase in time, a lot of overhead for not very good resolution of the problem. So now switching over into the 2D simplification for this nonlinear static study, now we're solving something with a pretty good representation of the geometry in about 20 seconds. Taking that one step further, where we get some really good refinement, the kind of refinement that we would expect to want to have for these types of thin members, the seals in particular. This would be a model that I would consider probably pretty close to being adequately have an adequately converged solution on the results. So you see we're up to 3,400 elements, and solve time still under 1 minute. So very doable with 2D simplification for nonlinear study types. So to sum it all up here, here's what we have shown you in terms of the savings that you get from the 2D simplification. There again, it's available if you are running Simulation Professional or above, and quite a bit of a benefit from using that functionality. So I've showed you the top 10 list. Here's just sort of a breakdown of it, what we've talked about. A lot of good functionality within the simulation tool. I hope that this has been a benefit to you, and I hope that you make use of some of this new functionality that's available to you that's in 2013. I'm going to show you some of those now. So for Simulation 2013, the things that have been changed or added, the interface has been massaged a little bit, worked with the folders and the navigation areas. Performance of some of the elements, in particular the beams and shells, have been improved, in particular in the way they bond to other members, other element types, when you have the mixed mesh. What's been introduced, and what will probably be the subject of another webinar in the future for you guys, is the submodeling has been introduced, where we can do what's called incremental meshing. We can mesh individual parts now. We don't have to remesh the whole model if we want to change something about a particular part, about how it's capturing the geometry. We can also run these submodeling studies where we take a larger assembly and break it down into smaller parts and look at in detail at some of the more refined areas where we can get extra refinement and dig into it a little bit further that way. Material is now variable in your design studies. If you know about design studies, you can vary things like the model dimensions, the mesh density, the loads. Now we can also vary the material. So if we want to do those what-if scenarios whereby we choose a different material, then that's now possible. Factor safety for selected bodies has been added. So you can look at individual particular bodies of interest and look at the factor safety for those. And we can also do results plots for selected entities as well. So looking at particular areas for the other results is now possible. I showed you the three-dimensional results mapping for shells. That's a new feature. And then the use of sensors, now they can be transient sensors. So that's the presentation for the day. That's all I had for you. If you need more information about any of this, or would you like any more information about any of the simulation products, please send us an email to info@mcad.com. If you're interested in training, we have the email address there where you can contact us. Just give us the time frame in which you'd like to attend a class. And then technical support. If you need support, just send us an email to support@mcad.com. That's all I have for you today. Thank you for joining the webinar, and I hope to talk to you soon. Goodbye.